Let us finally use this finite element method to solve this differential equation, which is valid over this domain, that is x goes from 0 to 1, and the boundary conditions are u of 0 is equal to 0, that is u at x equal to 0 is 0, and u at x equal to 1 is also 0. Looking at this boundary condition, we can say that these are the essential boundary conditions, and what we need to do is we need to obtain the solution of this given differential equation by considering three elements over the domain, and that is what exactly we do in finite element method. We do not solve this problem, we do not solve this differential equation over the entire domain, but what we do is we discretize it over into number of small elements, and then we try to solve it. Fine. And then in this case we'll be using Galerkin's weak formulation in this finite element method. So we know that the Galerkin's weak formulation or Galerkin's formulation is integral of weighting function multiplied by residual over the domain must be equal to 0. And then we know that the weighting function is nothing but the partial derivative of the displacement trial function with respect to the unknown parameter. And in case of finite element method, our displacement model will be nothing but u equal to n1 u1 plus n2 u2, or ni ui plus nj uj, and then the weighting function wi will be nothing but the partial derivative of vu with respect to ui, which will give us ni. And then similarly weighting function wj will be dou uj, which will be nothing but the shape function nj, and that is what has been written here. And then since there will be two weighting functions, I can group them together in this fashion. That is, weighting function will be nothing but n transpose, where n transpose will be somewhat like this. It will be ni and nj. So that is what we will do here. In place of weighting function, we will substitute n transpose, where ni and nj are this, which we have already derived this in our previous sessions, and this looks to be in terms of global coordinates. So the given domain, that is from 0 to 1, we will be dividing it into three elements, that is element 1, element 2, element 3, and the one of the typical element is shown here, which goes from xi to xj, that is with respect to global coordinate system, and let the length of this element be L. Now since they have asked us to consider at least three elements over the domain, now as we had seen earlier, it may be of equal length or it may not be of equal length, and that is totally up to us. We can say that this element is shorter compared to the other two, or these two are shorter compared to this, or whatever is the combination, or it can be even equal. That is totally up to us. So after taking this typical element, we can put this domain of this element now in terms of global coordinate as from xi to xj. In place of weighting function, we will be substituting n transpose, that is the weighting function, multiplied by the residual. This will be the residual, multiplied by residual dx will be equal to 0. And we know that when we say now on, whenever we use Galerkin's formulation or Galerkin's weak formulation, it is modified Galerkin method, and in that case, even before substituting this trial function, we integrate this weighting function multiplied by the first term of the residual by parts, so that we manage to reduce the order of this term. And exactly what happens here, after integrating by parts, we get this, wherein we manage here to reduce the order of this differential equation, that is from d square u to dx square, we will get du by dx. This is nothing but the integration by part from here to here. It is integration by part of these two terms, and then this term and this term will remain as it is, which we had seen in much detail in our previous videos. So in this in this step, while integrating it by parts, we end up getting this as our boundary term, and then before proceeding we'll have to take care of this boundary term. Now if you look here carefully, we have your du by dx, which is first derivative of this trial function, and then if I compare it with this differential equation, this will turn out to be natural boundary condition. And then in a given problem, nothing has been mentioned about the natural boundary condition. Both the boundary conditions are essential, so nothing has been told to us about the natural boundary condition. Only information which we have is about the essential boundary condition, and therefore the only way to proceed further from here on is we'll have to totally neglect this term, because nothing has been given about this term in the problem. So in that case we will neglect this term, and then this term, remaining three integrals, this term, first term, second term, and third term, can be rewritten in this fashion. And then if I take this on the right hand side, and if I switch the signs, that is the minus becomes plus, plus becomes minus, and then this side, this minus becomes plus. If I switch this sign, I will get this equation. Now how I have placed this equation is, wherever there are u terms, whether it is u or whether it is du by dx, all those terms, whichever term contains u and its derivative, I have kept it on one side, and whichever term is independent of this u, or whichever term do not consist of this u or its first derivative, and it consists of only x term, has been kept on the right hand side. And this will be known to you why we have done this exactly. So this term, first term, I will consider, this term I will consider as integral 1, second term I will consider as integral 2, and the last term I will consider it as integral 3. So I have this equation as I1 minus I2, which is equal to I3, and this is what we will be solving now in a while. So before this, we now is the time to assume a trial displacement function, and we know that for a linear 1D linear element, the displacement model is this is our displacement model, and we can write it in terms of matrix as ni nj times ui uj. Further, in the compact form, I can further even write this as n times delta, which we had seen last time. So this will be our assumed trial displacement function. Now let us consider this first integral I1. So what we'll do is we'll solve only this integral first, then I will solve the second integral, and then finally I will solve the third integral. And then I will substitute all these integral values in this equation here. So let us consider only this first integral I1. So this is the first integral I1, and then if you look carefully, I need here the derivative of the shape functions, derivative of shape function transpose, and then I want here derivative of u. Now the shape function transpose can be written as this way, because this is our ni, this is our nj, and the transpose of ni and nj will be a column vector. And then if I take the derivative of this term with respect to x, then I will get this as minus 1 by le, because this term will be treated as constant, so I will have only this term. And then since I am taking the derivative of this with respect to x, so let me do this one term here. So derivative of xj minus x by le will be equal to -1 by le. So that is what I have written here, and similarly here it will be +1 by le. So this term, wherever I have this term derivative of n transpose, I will substitute it with this term, and then where I have here du by dx, I will have to take u. I know that u is nothing but this term, and when I say derivative of u, I will have to take derivative of ni, derivative of nj, and these are nothing but the unknown values at the node I and j. Ui and uj are nothing but the values at node I, and value at and value at node j which are independent of x. So when I take the derivative of u with respect to x, I need not do anything to these values because these are the unknown parameters at the nodes. So but n depends on this value x, so I will have to take the derivative of this ni and nj. When I say, when I have this term du by dx, it means nothing but it is derivative of uh, shape functions ni and nj and multiplied by this term ui uj. So if I do this again, just now we had done this, so derivative of ni with respect to x will give me minus 1 by le, and this term will give me plus 1 by le. So I just need to substitute this now. In place of this term, in place of this term, I will substitute this here, and in place of this term, second term, I will substitute this here. And then this is now 2 by 1, and this is now 1 by 2, and if I multiply them, I should get a matrix of 2 by 2, and that is what exactly we'll get here, because if I multiply minus 1 by le with minus 1 by le, I will get 1 by le square. Then minus 1 by le multiplied by plus 1 by le will give me minus 1 by le square, and similarly this multiplied by this, I will get minus 1 by le square, and this multiplied by this, I will get plus 1 by le square. So this is nothing but our I1 term. Now if I further integrate this with respect to dx, this will be nothing but x by le square. This will be minus x by le square. This will be again minus x by le square, and this will be again x by le square, and the limit will go from xi to xj. And if I substitute this here, I will get, then finally I will get this as xj minus xi by le square. This will be minus xj minus xi by le square, and then similarly this will be minus xj minus xi by le square, and this term will be xj minus xi by le square. And then further, if I substitute what the value of this xj minus xi, I know that xj minus xi is nothing but the length of this element le. Fine. So if I substitute that le here, if I substitute this as le, this one le length of the element and this one will cancel, and finally I'll get it as 1 by le. This will be minus 1 by le, this will be again minus 1 by le, and then this will be 1 by le. So if I remove this 1 by le out, finally I will get this I1 as this term. Now let us consider the second. So this is what I got here in place of I1. Now I need to find the value of I2, that is of this integral. So if I consider, rewrite this value of this integral I2 here, this is the integral I2 which I have taken from this is the I2, and I2 has nothing but n transpose of u, but n transpose is nothing but this xj minus x divided by le. So we have this xj minus x divided by le, or you can just write it as ni and nj, and u is nothing but this ni nj multiplied by ui uj. So that is what has been written here. And then if I cross multiply this, again this multiplied by this will be ni square, this multiplied by this will be ni into nj, this multiplied by this will be again ni into nj, and this multiplied by this will be nj square, because since this is 2 by 1 and since this is 1 by 2, I'll get finally the matrix as 2 by 2, and this we have kept as it is. These are the unknowns at the node I and node j. So this we have kept as it is. Now if I substitute this value of ni, that is xj minus xi divided by le square, and similarly if I go on substituting this, and then if I try to integrate, it will take a lot of time. So what we can do is we can use here one integral formula, and this is a very useful formula which will make our integral very easy. So how to use this formula is, if I have here two terms n1 and n2 with the power of alpha and beta from the domain xi to xj dx, I can integrate this directly as follows. So this will be alpha factorial multiplied by beta factorial divided by alpha plus beta plus 1 factorial multiplied by these limits xj minus xi. So this formula will be very useful to evaluate this matrix. Within no time we'll be able to evaluate this matrix if we substitute the values of the shape functions here, individual shape functions, and then if I try to integrate, it will take us lot of time. So what we will do is we will use this formula to evaluate this matrix. So to use this formula, what we can do is, now let us consider only this term, only the first term. Let us consider only first term. The first term is nothing but integral xi to a xj ni square times dx. These are the constant terms, so we will not include them in this integral. So in this case, now I have here only one n, I have only n1, so this term is not present here. So in place of alpha I have 2, in place of beta I have no value, so I will just, so this is just 0, so 0 factorial is 0 factorial is just 1, so I need not write this. I need not write this. And here again this beta will be 0 because there is no beta value here, but alpha is again 2, and then we have this plus 1 factorial. So this is 2 factorial divided by 3 factorial multiplied by this term xj minus xi. So xj minus xi is nothing but it is the length of the element le, because if we have a element here of coordinate xi and xj, so xj minus xi will be nothing but the length of this element le. So I will write this term as le, and 2 factorial divided by 3 factorial will give me 3, that is 2 factorial divided by 3 factorial will be nothing but 2 divided by 3 into 2 into 1, which will give me this 2 and this 2 will go, which will give me 1 by 3. So this term becomes le by 3. Similarly, if I integrate this term, it is nj square, so it will be again same thing, it will be same thing as this, the procedure will be exactly same. Only thing is here in place of alpha we'll have beta as 2, alpha will be 0, so 0 factorial will be again 1. So again we'll get the same thing, 2 factorial by 3 factorial, and it will be xj minus xi. So even this term will give me le by 3. And then finally I have this integral of ni nj from xi to xj dx, and if I do that, now here I have alpha value as 1, beta value is also 1, and this will be again 1 plus 1 plus 1 factorial. So this gives me 1 factorial by 3 factorial times xj minus xi. Now xj minus xi is again length of the element le, and 1 factorial by 3 factorial will be nothing but 1 by 6. 3 factorial will be 3 into 2, that is 6, and 1 factorial will be 1, so this will be le by 6. So now, and then similarly again this term is also same, it will be also le by 6. So I have now got the values of all this term. This will be le by 3, le by 6, le by 6, le by 3. So if I substitute it here, if I substitute all this here, so I will get this I2 as this times ui uj. Since I had used this integral formula, I could very quickly evaluate these terms. Now if you try to substitute the value of ni as x j minus x divided by le, and if you try to integrate this from xi to xj dx, you will get exactly the same value as le by 3, but it will take a lot of time, it will take much of your time in just evaluating this integral, and that too you will get the same answer. So rather than that, we can straight away use this formula, and it is always advisable to use this formula here. So I get this term as I2 as le by 3, le by 6, le by 6, le by 3 times ui uj, and then if I bring out this le by 6 common from this matrix, I will get this as 2 1 1 2 le by 6 times ui uj. So I have been able to evaluate I2 also, and our equation was I1 minus I2 is equal to I3. So I had found what is I1, then now we have found what is I2. Now let us evaluate what is I3. So I3 will be I3 will be this was our I3, and here I want now n transpose time x. So n transpose is nothing but ni nj. And then since we had this as our displacement model, similarly for x I can write the equation as this. Only thing is, in place of u I need to replace them by x, that is by coordinates, and then I will get this as ni nj times xi xj. So if I, in place of x, if I substitute this, and in place of n transpose, I know that I can write it as a column vector of two shape functions ni and nj. And then if I multiply this, cross multiply this, again I will get here same equation as this. Only thing is, here in place of ui and uj I will have xi and xj. And then same matrix, if I evaluate it using this integral formula, I will end up getting the same values, le same matrix I'll get. And then if I remove that le by 6 out, I will get this same equation again. You may try this, because this will be nothing but xi to xj. This will become ni, this matrix will be ni square ni nj ni nj, and this will become nj square nj square times dx. And since we had already evaluated this matrix here, I need not do all these things again. I can just write these values directly. And then finally we had this equation I1 minus I2 equal to I3. Now I have been able to find the value of I1, I2 and also I3. So if I substitute them here, I will get this equation. This is the equation which I wanted. Now further, if I remove this ui and uj term common outside of this, so I will get this as our matrix. So I have this term times ui uj is equal to this term. Now if you look carefully, I can this quantity I can write it as kind of a k matrix. This quantity I can write as if it is a delta matrix, and this I can write as if it is a f matrix, that is a force matrix. And this is nothing but the familiar equation, the Hooke's law, right? Force is equal to stiffness times displacement. So this is also, this equation will also give us the Hooke's law kind of equation, that is force times forcing function is equal to stiffness times the displacement, and displacement is what we need to find for the given stiffness. So this quantity is a stiffness like quantity, this is the displacement like quantity, and this is a forcing function like quantity. So that is why initially, while adjusting those integral term, I had kept all the u terms together, and I had put this x term on the right hand side of this equal to sign, so that I get on one side I get all the delta terms or the displacement terms together, and the whatever is remaining multiplied with that becomes the stiffness type quantity, and whatever is there on the right hand side with x becomes the forcing function like quantity. So once I get this, now our question was to solve this differential equation for three elements. Now what I have done here is, I have taken all the three elements of equal length, 1 by 3, 1 by 3 and 1 by 3. Now this is totally up to us. I can take whatever length I want, but it should be three elements since it was asked in questions. But here I have taken the equal length. If you want to capture some good data here at the boundaries, then you can probably keep this element length small and you can increase this element length, or you can even go for 5 to 10 elements, whatever element we want. Once I get this equation, this is nothing but our FEM finite element method equation. And to be more precise, this is the element equation. Once I get this finite element equation, you can discretize this entire domain into the n number of elements you want. Fine, because once I get this equation, I can just go on discretizing this total domain with any number of elements that I want. Now let us see, for three elements which was asked in question, and for equal lengths which I have considered to be equal lengths, what will be our solution. So let us divide this into three equal length elements, and then I need to find here now what is k matrix, what is delta matrix, and what is f matrix. Now let us see first what is k matrix. Now let us consider this element 1. now for element 1 the length is 1 by 3, so wherever there is LE for K matrix I will substitute the length as 1 by 3. That's it. And then I will write this as it is, and only in place of LE I will substitute it by 1 by 3. So here I had LE, I have substituted by 1 by 3. Here I had LE, I have substituted by 1 by 3. And then if I take this, if I multiply this 3 inside, I will get this as 3 minus 3 minus 3 3. And if I multiply this 18, 6 multiplied by 3, I will get this as 18, and this is kept as it is inside. Now what I will do is I will multiply and divide this matrix by 18, so that I get 1 by 18 common. And then if I take that common outside, and if I do subtract this matrix from this, I will end up getting this matrix. So this is the stiffness matrix K1 for first element L1. And now if you look at this carefully, since all the lengths are equal, even for element 2 K2, even for element 2 the stiffness matrix K2 will be exactly same as this, because the length of this element what we had taken was same, right? 1 by 3 1 by 3 1 by 3. So the stiffness matrix for K2 will be also same as this, and stiffness matrix K3 will be also same as this. So I got K1 matrix as 1 by 18, 52 minus 55 minus 55 52. Similarly I got K2 also. Similarly I'll get K2 also as 1 by 18, and same thing, 52 minus 55 minus 55 52. And similarly I'll get the matrix for K3 also. But this matrix K1 matrix is applicable only for element 1. This matrix is applicable only for element 1, which will take care of node 1 and node 2. So this matrix will take care of node 1 and node 2, Similarly, let me say this as K2 and this as K3. So K2 will take care of node 2 and node 3, because K2 is nothing but a stiffness matrix of element 2. So this will take care of node 2 and node 3, node 2 and node 3. Similarly, this K3 stiffness matrix of third element will take care of node 3 and node 4. So this will be node 3 node 4, node 3 node 4. And these are now the three individual element level stiffness matrix K1, K2 and K3. Now I will combine it to frame the stiffness matrix for this entire domain, that is from x equal to 0 to x equal to 1. For the entire domain, if I want to combine this element level stiffness matrix, that is three stiffness matrix K1, K2 and K3, I can frame it in this fashion. I will get the total size of the element as 1 2 3 4, because there are four nodes, 1 2 3 4, and the degree of freedom of each node is 1. That's why I'll get this as 4 by 4 matrix, 1 2 3 and 4. This will be 4 by 1 2 3 4, 4 by 4 matrix. And then 1 by 18 is common for all three matrix, which I have taken it out. Now here in this place, 1 2 and 1 2, 1 2 and 1 2, that is this term, this term, this term and this term, I have here 1 2 and 1 2. So this will be 52 minus 55 minus 55, and this will be 52, this will be just 52. And then I have here the element level stiffness matrix for element 2 as this. So I have here 2 comma 2 element, that is 52. So here also 2 comma 2. So I will have here one more 52. Then again here I have 3 comma 2 as minus 55, 2 comma this 2 comma 3 as minus 55, and then 3 comma 2 as minus 55, and then here I have again 52. So here this 52 and this 52, that is 2 comma 2 of K1 and 2 comma 2 of K2, 52 and 52 will become 52 plus 52 will become 104. Similarly here this 52, that is 3 comma 3 of second matrix and 3 comma 3 of third matrix, third element, will become again 52 plus 52 will become again 104. And this 55 minus 55, this minus 55 I have written as it is, and this 52 again I have written as it is. So this is how we can combine the element level stiffness matrix to obtain the global stiffness matrix, which is nothing but the stiffness matrix of entire entire domain. So I have been able to evaluate the stiffness matrix for this entire domain by calculating the stiffness matrix for each element first and then combining them to get the global stiffness matrix which will be valid, which will be applicable for this entire domain. Now let us try to evaluate this force matrix, this matrix over this entire domain. And again our methodology will be same. First we will calculate the force matrix for the first element, then we will calculate the force matrix for second element, then we will calculate the force matrix for third element, and then we'll combine them to obtain the global force matrix. So the force matrix is given by this equation. Now let us say for this first element, this force matrix will be, LE will be, again for first matrix it is 1/3 1 by 3. So 1, if I substitute value of LE as 1 by 3, so it will be 6 multiplied by 3, I will get this as 18. This will be as it is 2112. Now xi and xj for first element, if I look at this our entire domain carefully, xi and xj for first element, this will be xi and this will be xj. Then the value of xi, these are nothing but xi and xj are nothing but the global coordinate system, and then x value of xi at node 1 is nothing but 0, and value of xj, that is at node 2, is nothing but 1 by 3. So in place of xi I will have to substitute 0, and in place of xj I will have to substitute 1 by 3. Now if I just multiply this matrix with this matrix, this is 2 by 2 and this is 2 by 1. If I multiply them, I should get a matrix of 2 by 1 again. And then if the same thing happens here, if I multiply this with this will become 2 multiplied by 0 will be, this will become 2 multiplied by 0 plus 1 multiplied by 1/3, and then this will become 1 by 3. That is what I have written here. And then if I multiply this with this will become 1 multiplied by 0 plus 2 multiplied by 1/3, which will give me 2 by 3. That is what is written here. And then if I bring this 3 out common, I will have to multiply it by 18, and this will give me 1 by 54 times 1 and 2. So this is what I get for element 1. The force matrix for element 1 will be this. Now force matrix for element 2, again the length will be same, 1/3. So if I substitute 1 by 3 here in place of LE, I will get that as 1 by 18, and then this remains same, 2 1 1 2. But now in place of xi and xj for element 2, xi is nothing but 1 by 3, whereas xj is nothing but 2 by 3. So in place of xi I will have to substitute 1 by 3, and in place of xj I will have to substitute 2 by 3. And if I do that, and now if I multiply this will be nothing but, this will be 2 multiplied by 1/3 plus this 1 multiplied by 2/3, and if I do that I will get this as 4 by 3. And similarly if I multiply this with this, I will get it as 5 by 3. And then again if I remove this 1 by 3 out, that will give me 1 by 54, and what will remain inside is 4 by 5. And similarly the forcing function or the force matrix for element number 3 will be, again it will be, this will be 1 by 18, because LE I will be substituting it as 1 by 3. I will get this as 1 by 18, 2 1 1 2. And finally this xi and xj will be, for element 3, xi will be 2 by 3 and xj will be 1. This 1 I can also write this 1 as 3 by 3, just for the multiplication purpose. And then if I multiply now this with this, I will get this as 7 by 3, and if I multiply this with this, I will get this as 8 by 3. And then further if I remove this 1 by 3 out, I will get this as 1 by 54, and what will remain inside is 7 and 8. And then again if I club them together to form a global force matrix, which will be in the following fashion: the F1 will take care of node 1 and 2, it will take care of node 1 and 2. F2 will take care of the node 2 and 3, and F3 will take care of node 3 and 4. And finally I will have your force matrix as node for node 1 2 3 4, as this will be 1 by 54 will be common. Here 1 and 2 I have 1 and 2, 1 and 2. Here for 2 and 3 I have 4 and 5, so this will be 2 plus 4 and this will be 5. 2 plus 4 will give me this 6. 1 will give me this 1, then I have here 5, and here I have 7 and 8, so this will be 5 plus 7 and 8, so 5 plus 7 will give me 12, and this 8 will give me 8. So I get finally this value 1, 6, 12 and 8, and multiplied it by 1 by 54. So this is my global force matrix. So I have been able to obtain the global stiffness matrix and global force matrix. So if I club them together, if I bring them back, so our equation will be this was our equation, F is equal to K times delta. So in terms of matrix form, I can write this as K of global times this delta, which will be ui, u1, u2, u3, u4. That will be the values at those four nodes, u1, u2, u3, u4 delta, which will be equal to this forcing function F, or the force matrix F, and now it will be global level. Earlier it was all this were element level, but now we'll be using this global level. And then finally, if I substitute it, I will get this. This will be our final global equation. Global system of equation will be this. Now if I apply this boundary condition, now the boundary condition which were given to us was u of 0 is 0, and u of 1 is also 0. So that means u is 0 at x equal to 0, and u is 0 at x equal to 1. So at x equal to 0, at x equal to 0, we have this as, we have at x equal to 0, here I'll use this, at x equal to 0 we have value of u1. So u is 0 at x equal to 0 means, actually speaking it should be u1 which should be 0, and then u is 0 at x equal to x1. So at x equal to x1 u is 0, that means truly speaking u4 should be 0. So this is our boundary condition, u1 is 0 and u4 is 0. This was given to us, right? This was given to us. So again I'll repeat, this u is 0 at x equal to 0, which tells me that u1 is 0 and u is also 0 at x equal to 1. That means it tells me that u4 is 0. So u1 is 0 and u4 is 0. So this term is 0 and this term is 0. Now if these two terms are 0, I can straight away neglect this first row, fourth row, and then first column, and then fourth column. This is one way of handling the boundary condition, and there are other ways also, but this is one way of handling the boundary condition. If that is the case, then what will remain with me is 1 by 18 times only these terms will remain. So that is what has been written here, 1 by 18 times 104 minus 55 minus 55 104 times these terms are 0. So what will remain with me is u2 and u3 equal to 1 by 54 times only 6 and 12 will remain, because this is, because of boundary condition these terms are gone. So what will remain is 1 by 54, 6 and 12. Now if I simplify this further, I'll get the value of u2 as this and value of u3 as this. So this is how we have been able to solve the problem using finite element method. And the approximate method which we had put in this finite element method is the Galerkin's Wick formulation, or modified Galerkin method. So because since we had divided this domain into only three elements, that is one element 1, element 2 and element 3, and these nodal values were already given in boundary condition, that is this is 0 and this is 0. The only unknown values which remained here was only two, u2 and u3. Now if I had divided this with four elements, then I would have had here, so suppose say I had divided this into say four elements, this was our one element, this was our one element, this was our third, and this was our fourth element. We would have had here three unknowns, unknown 1, unknown 2 and unknown 3. Anyways, but since we have got already these values, further if I want to find the value anywhere in between, what I can do is I can straight away use the shift function. I know that the displacement model is u is equal to n1 u1 plus n2 u2, or ni ui plus nj uj. And if that is the case, here in this case, if I want to find if I want to find say value of u somewhere here in between, what I can do is I can write this as n2 u2, this will be n2 u2, and this will be n3 u3, this will be n3 u3. And then further I can write this n2 as x3 minus x by le times u2, plus this n3 will be x minus x2 divided by le times u3. And then if I know already the value of u2 and u3 which I have found, and then suppose say I also know the coordinates x2 and x3. I know the value of x2 and x3. x2 is 1 by 3, x3 is 2 by 3. So this values I know. This is x3 is 2 by 3 minus x divided by le is 1/3, u2 is what we have found, 0.0549. And then this will be again x minus, this will be x2 is 1/3 times le is 1 by 3, and u3 is 0.0675. So if I want to find u now anywhere in between this, say let us say exactly at the center, so exactly at the center, or x from x as a global coordinate will be 0.5 at the center. So x will be, I can just substitute this x as 0.5, and this will give me value of u at this point at x equal to 0.5. So this is the benefit, or this is the use of the shape function. That is, if I can find the values of nodal parameters, that is u2 and u3 here in this case, by finite element method, and if I want to find the values at anywhere in between this element, then I can use this displacement model, I can use this shape function, and I can find the values anywhere in between the element.